Prof. Xin Ma from the Harbin Institute of Technology, talking about almost elementary groupoids and their sister algebras.
Thank you, Xin. Thank you for the introduction, and thanks a lot for thank the organizer for providing me an opportunity to be here to give a talk here, and this is my first time in UK. So today I would like to talk about some structure theory about groupoid and its relation to the structure theory of the six algebras. So this is based off the joint work with Jianchao Wu. Okay, so for the setting, so let G be always locally compact house-orbital groupoid and with a compact unit space. And in the case that your groupoid is ample, then what is the so-called the elementary subgroupoid is compact open principal groupoid with the same unit space with the original and the groupoid. So and such groupoid automatically admits decomposition to a collection of the bisections, and it looks like a sum of the matrix. So for example, it satisfies these relations. So VIG L, okay, I forget some L here. So VIGL is serves some like the EIJ, like the basis of the matrix, right? So somehow it's like the sum of the matrix. So as a picture, so we have this the picture for the decomposition of this elementary groupoid. So we have several castles, and you have several towers. So it forms a castle, and on each tower you have several you have several bisections connecting them. Okay, so and they are destroyed. So on the unit space. Okay. Now, of course, the bisections are also from a destroyed boundary. Okay. So why we care about that? So in general, so such elementary subgroupoid will give us the matrix algebra. So as one may imagine. So for example, so for the full, the elementary groupoid, or it's just like the full equivalence relation on the finite side. It just gives us the matrix algebra on the complex numbers. And for the elementary groupoid in this picture, so it just gives us the matrix of the continuous functions. So here I just assume that all VIIN is just the closed set, so or maybe the compact open set. So therefore, we just consider the continuous function, all continuous function on that. So we have this form. So later we will see that. So if the VIIN is just like the open set, so then you have to consider the C0 version of this algebra. And so therefore we can regard that such an elementary subgroupoid as a finite approximation of the original groupoid, and therefore it gave us like the finite approximation. In the system level, so it still serves as a finite approximation of the groupoid system algebra. So that's why we care about it. Okay. So I don't know. And to my best knowledge, okay, this is maybe the first notion about a large elementary groupoid. Okay, you suppose you have a groupoid, so and you have a very large elementary subgroupoid, and this gives us a very good structure of our groupoid. So this is called almost finite, introduced by Matri. So the motivation is to study the homology theory and topological fold groups. Okay, so what is so we see an ample groupoid is almost finite if for any epsilon and any k, k is a compact set, we can find a large elementary subgroupoid. So as David mentioned, so you have some ownership, okay, for your decomposition of the elementary subgroupoid in the picture I have mentioned. Okay. Then here, so this condition is looks like the Bohner condition for the minimal groups, and this indeed sees some amenability, but unfortunately it is not the topological amenability. It is so-called fiberwise amenability. So also introduced by me and Jianchao. So, but due to the time limits, I cannot explain everything. Okay. Okay. So and then David refined this notion to the dynamical systems, and so David explained a lot. I mean the techniques here to the minimal free systems without the assumption on without the the dimension without assumptions on of the emptiness. Okay, so he can work on the higher dimensional space, and you still have some decompositions of the elementary group point. So as he draw a picture here, so and he allows a small remainder. Okay, and then he can prove as he also described how. Okay, so your reduced first product is this stable, and therefore you have all conditions for this algebra to be classified. Okay. However, so the idea of his proof cannot be directly applied to the general groupoid setting. So as he mentioned, you have to do the Ornstein-Weiss cost-tellings of the large Fourier set into the small Fourier set. It is still unknown how you can implement these techniques in the groupoid setting. Of course, somehow I believe somehow one can do that, but it's still very hard. So because this is mainly due to the fiberwise nature of a groupoid. So you have a different you have different units. So the fibers are different. So in the geometric sense. So you have very different geometric structures. So unlike the transformation groupoid, so in the transformation groupoid, so every fiber is isomorphic to your acting group. So you have the same structure, okay, same geometric structure, but in the general groupoid case, no, you don't have that. So typically cannot do such a techniques. Okay. But it is still a question. So how to determine the stability of the groupoid system algebras? And in particular, is it true that for almost finite groupoid, okay, whether it's reduced the groupoid system algebra is this stable, right? It is a very natural question. And also motivated by Xin's result, he constructed the groupoid model for all classifiable system algebra. So here's another natural question. So is there a groupoid theoretical characterization or recognition for all system algebras? For all classifiable system algebras. Okay. So now we have we decided to invent a new language to describe everything. So but also due to time limits, I cannot give you the new notion. So let's keep our old notion using so-called multi-sections introduced by Nakashevich. Okay, so basically just describe a tower, okay, in a groupoid. So you have just one tower, okay, but he calls it a multi-section. So indexed by some finite sum. Okay. So suppose we have the collection of disjoint towers, then we call it his castle. So that means we have several multi-sections, okay, which forms a castle, and this gives us a groupoid, and we call it the castle groupoid. Okay. And then now we do not want to use the Fourier shape of your elementary groupoid. So instead we introduce some new things. Okay, so we use two castles. Okay, instead just only one castle with a Fourier shape. We call it extendability. So what does this mean? So suppose we have two castles. One is a C and one is a D. Okay, so and the K is a compact set. So now we do not ask that each C has a Fourier shape with respect to K. Instead, we say that when you apply the partial dynamics of the K on your C castle, then every dynamics, every information of this dynamics will be still encoded in a very good way in another matrix, which is a larger one, which is called D. So, and this condition just for simplicity, you don't have to assume that. So, but for simplicity, I add here. So here's a picture. Okay, you have so the blue one is the C castle, and the red one D castle. Okay, you can see here. So first they have some overlap. Okay, so the length of the D, the D towers is larger than the length of the C tower. Okay, they have some, they overlap some, and for any gamma in K, and if we want, if the gamma wants to move some point, okay, from the C, I mean the point comes from the sea level, then you can see that you can still do you can still use some elements in the D castle to do the same thing. So that's how somehow this is that's how the extendability. Okay, then what is almost elementary? So so given any K, given any compass at K, and because now we are working in a not necessarily ample case, so we still allow the small remainder. And with I mean, so this notion is similar to the almost finiteness, I mean, introduced by David. So we also need the small level. Okay, so but the because we still want to work in maybe in non-separable case, so we just use covers to control. I mean, how large is your levels? Yeah. So first, I mean, given the K and O and the open cover way, so we can find the two castles, okay, C and D. First, so it should satisfy that C is K extendable to D. And next, so the D level is smaller. So D refines your cover weight. So that means your level is small, and you allow the small remainder. So okay, that's a condition. So we do not need the ownership condition. And actually, so the matrix almost finiteness is equivalent to the almost elementariness plus the so-called fiberwise amenability in the minimal case. And as a mass theorem, so we have proved that. So if your G is a locally compact host of sigma compact, so we do not need the separability condition. So you tell minimal group point compact space. So and suppose your group point is almost elementary, then your CC algebra is simple and trivially this stable. Okay, so as I said, so this proof is not based on the idea of the David mentioned. So you have to do some. Yeah, so somehow we also need to do some partition of the shapes, but not in a photon way. So and you need to give some the decay functions on the levels. Okay, so that you can make the commute almost commuting conditions work in the definition of the trivial stability. Okay, so as a corollary, as you can imagine, if you add some standard assumptions like the separability and nuclearity, so then you will have the stability, right? So that it is classifiable. So therefore, so for the matrix, almost finiteness, as I said, so almost finiteness will imply in the almost elementariness. Definitely, it implying your reduced frequency algebra is trivial stability. H is trivial stable, and if you add another assumption that your group point is minimal, topological minimal, and a second countable, then is CC algebra is trivial stable. Okay, so for our second question, so okay, maybe so this is kind of the answer of the answer of the second question. So almost elementariness and almost finiteness indeed is kind of the recognition of the stability in the group point level. Then we would also to say, so can we have a lot of examples? So because maybe you will feel that the definition is kind of a technique. So our simple idea is to try so all group point model in the market is for the classifiable CC algebras, but so except for Xin's examples, for other ones, I mean, to my best knowledge, to my best ability to search, so everything except for his models are all almost elementary. So I will explain. So first, so one cannot expect that any group point model for classifiable CC algebra is almost elementary. So here's a kind of example. So due to the Joseph and the Hirschberg and Chen Chao, so some the so-called allosteric profinite actions, okay, because such actions is not essentially free. So therefore you have an obstruction for your group point to be almost elementary, or almost finite. However, so one can show so for any cross product, okay, so if your space is has a finite dimension and your gamma is a minimal, it's a classifiable if and only if it has a minimal topological principal and minimal almost elementary groupoid model. So actually, so the proof is not hard. So it's just times the groupoid model of the geometry algebra on the right, and then you just like David also mentioned. So if you have the product system, if one has a small boundary property, then the whole system has small boundary property. Similar techniques. Okay, so and a large class of such models comes from the partial action, as Karen mentioned yesterday. So here's a definition of the partial action. So somehow that means you cannot allow that your group moves. So it means so the action is not defined on the whole space. Okay, so you should allow some holes that your group elements does not move anything. Okay, it's just not defined there. Okay, and from the partial dynamical systems, one can still define a transformation groupoid in a similar way, but here you have to adjust your domain. Okay, just comes from the point that you have defined your action on. Okay, and so for the orbit breaking construction, usually comes from this way, right? So especially for the z action, you just for the generator one, you just eliminate just one point. But that means for other group elements, you have eliminate several other points, right? So then you have basically you have this definition. So for any g in z, so your domain for this g as this form, you have to eliminate several points to make your partial dynamics work. Okay. But anyway, so in the in the global z action, one can define the Kaktani-Rohani partition, so which give us the almost finiteness in general. But now, if you just eliminate several finitely many points, then it doesn't matter, right? So in this picture, so suppose this part is a Kaktani-Rohani partition for the global action. And now you have several red points that there's no definition for your group action. You just eliminate them, just sort them away. And even you can sort them with a small neighborhood so that you can still do everything in your group point. So because if you throw them away by comparison, you can still move them by using some other group elements to a very small neighborhood, to a very small open set. So you still have the almost elementary there. So therefore, so we can show that. So these examples, okay. So first, the examples the Karen mentioned yesterday, and also the Jack's groupoid model for the Kirchberg algebras, and of course, the Clark, Fletcher, and Huth. So also, so make it to be the unital word. So we have a unital, so the groupoid model for the unital Kirchberg algebras. And also the original AF groupoid for the simple unital AF algebras. And we can show that. So these groupoids are all almost elementary. So therefore, we have, suppose you have a cis algebras. You don't know whether it is classifiable, but at least you can compute the K theory there. And I suppose your cis algebra has the K theory, okay, coinciding with these algebras. Yeah. So that means that the additive inversion is of these forms. Okay, then we can have this result. So suppose you are A, okay, you see in this class means that your A, the additive inversion of A is of that form. Then A is classifiable if and only if it has a locally compact Hausdorff-Etel minimal second countable topological minimal almost elementary groupoid model where the unit space is compact. So somehow this is a kind of the groupoid level recognition of the classifiability of the groupoid cis algebras. Okay. And of course, as a corollary, so all UCT self-absorbing cis algebras always has such a groupoid model, as an almost elementary groupoid model. Okay, so okay, so that's all for me. Okay, thank you.
Questions for Tim?
Go back to the slide before the partial difference, please.
Yes.
The partial
This one or this one?
before that. Okay. Maybe another one.
This one?
No, back.
Back, okay.
You had a different, it's not this one, you had an if and only if statement, like the sister algebra cross product is classifiable. If and only if.
Oh, you mean this one, right? This one, right? This right up? This one.
Yes, right, but why is this if and only if, isn't this just a property, aren't these all classifiable?
So that means so.
X is finite dimensional?
Yeah, X is finite dimensional.
And you're talking about minimal free actions, no?
Yes, that's of course. So, yeah, maybe we should add some assumptions here, like it's minimal free, minimal topological free. Yeah, maybe I forgot to add in the standard assumptions here.
Okay.
Yeah.
Thank you.
But I say so it's a classifiable if and only if. So if you assume it is classifiable, then you have everything what you want to there, right? So, like if it's classifiable, that means this is nuclear and simple. So then you have a minimal topological free and minimal topological minimal if I checks result.
But I mean, if it's classifiable, then this groupoid model might not be related to the.
No, maybe not. It's just it's just like some techniques there. So actually, so what we have is something okay. You tensor Z and you obtain the groupoid model for this one. Okay, and if this is classifiable, then it's just isomorphic to itself, right? So that's a technique. So actually, so when we have the groupoid model for this one, it definitely maybe not the original one. Okay, and actually here's a counter example. So the original one is not almost elementary. Yes, Drew?
Could you go back to the slide with the Elliott invariant? I think it was the second to last slide.
Any more? Maybe, yeah, maybe. This one?
Yeah, before it there, Lyrical C-star algebras with Elliott.
Invariant that of the C-star algebra, that's.
Where's the trace space? I'm missing something.
Uh,
Part two there.
so yeah, only this one you have a trace here. Maybe unit, yeah.
In part two there, I mean.
Actually, so this corresponds to purely infinite case.
Okay.
Yeah, so you have no trace here.
Diego?
Yeah, can you go back to the next one? Go back, okay, yes, this one, no, sorry, minus forward. This one? No, it agrees to last this time.
Not the usual.
Okay, the last three.
Yes,
Okay.
so can you say a few words on how you get rid of the twist?
Twist. Because in our condition we don't have twist, but if you add twist, this will work, I believe.
Okay, so this groupoid model that you construct is twisted.
It's not twisted.
Yeah, but then,
Because the groupoid model is just comes from this one, so there's no twist there.
okay, but
Yeah, we just verify almost elementary for this groupoid models. So because there's no twist here, so yeah. But of course, so if you just want to add a twist to this groupoid space algebra, it doesn't matter. So it's just yeah, the same techniques actually.
Let's section again.